Okay, hi. Right, so today I'm going to talk about using monads to talk about effects more in the way that we implement them in a compiler than how we use them in high-level languages for structuring our programs. Okay, so let's talk about monads. Okay, so monads have been, I'd say, enormously successful. For the purposes of simulating effects in high-level programming language, right? So here, high-level programming language. This is the actual slide. Okay, and so what is a monad? So a monad is some type constructor, so it takes types to types. And we have these functions, return. And intuition is that we think of a value of the type tx as a first-class value representing an effectual computation, okay, that returns x's values, okay? And so the abstract functions that we always have for any such notion would be that we can embed a pure function, we can embed a pure computation into an effectual computation, and given a function that takes x values to y computations, we can extend that to be a function from effectual computations on x to effectual computations on y. Okay, and that's the foundation for monadic bind or let binding in normal syntax, right? And so, of course, there's a bunch of equations also that should hold that are very familiar to all of us, so I won't bother going through them. And also, there's this extra thing, which is that actually everything is a strong monad, which I also won't talk about because it doesn't make much difference. But everything is actually strong and all of that, and satisfies equations in this talk. Okay, so so for example, the two examples I'm going to go use a lot in this talk, we have the so-called exception monad, or in Haskell this is either, in ML this is called result, right? Where we say an effectful, a model, we could say, of a computation that might raise effects is a sum type, right? So either A, I return the A, or I choose to return the error, right? Which we can think of as raising the exception, right? And then return is just in left, and extension is basically handling. And then the other one is the state monad, right? Where we can simulate the presence of state in our high-level language, right? As just functions that take in an initial state and output a final state alongside the actual result of the computation. And it's easy enough to implement return and bind for those as well. Okay, but so these simulate the effects, quote unquote, in the high-level language. But what about the real effects, right? When we're actually implementing this language in a compiler, what do those real effects actually look like? Well, let's think about these two examples, right? So when I'm compiling exceptions, right, the implementation using the sum type responds to this over here on the left. So I'd say, okay, my model is this type A plus E, right? And then what does the stack look like for function raising an exception? Well, then it would just have basically a continuation for either an A or an E, right? And so there's a problem with this implementation, which is every time that you raise an exception, you're going to return to the continuation. The continuation is actually going to have to branch. Did I return the result A, or did I raise an exception E? Right? And so it's not a very efficient implementation. Okay, and that leads to a very closely related but more efficient one, which is called the double-barreled continuation implementation, where we say, well, when I'm raising an exception, I always know on the stack there's going to be a success continuation, which is where I send the A values, or an error continuation, which is where I send the errors, right? And then actual exception raising come from composing these things together, right? But then, if you actually Googled how do I implement exceptions, or how does C++ implement exceptions, you're going to get something that looks like this on the right? Where it says, okay, well, when I have a computation, when I'm compiling a program that raises an exception, then the stack is going to at the top have the return address, which is sort of like this success continuation, right? And I'm not going to have an error continuation on every stack frame. I'm only going to have them in some stack frames. And so when I raise an exception, I need to actually search through past all of the stack frames and find eventually where the handler was actually installed. Okay? And so Yeah. Oh, and then if we talk about state and compilation, well, we don't usually think about it in terms of functions at all, right? But for example, if we had a mutable variable in our source programming language, x, and I mutated it by assigning 5 to it, well, then I would assign that to, then I would pick somewhere in the actual machine state to represent that variable, right? So maybe I store it on the stack, right? And then this mutation is actually moving 5 into that location in memory. Or maybe I store it in a register and then I just move 5 into whatever register I picked for x, right? And so we get this weird situation where, you know, monads are very nice for talking about effects in high-level languages, right? But they don't seem all that connected to the actual implementation that we do in practice, right? So when we talk about a monad, we were talking about first-class values. But when we talk about compiling them, we're always talking about things like continuations. We're talking about the structure of the stack, the invariance on the memory, and on the registers, okay? And basically what I want to talk about today is that by taking a variation on the idea of a monad, okay, we can talk about these things in terms of monads, okay? And the correct version is this idea of a relative monad in call by push value, okay? So the basic idea is that so the first part of the basic idea is that monads are too high level, okay? So if we look at the idea of a monad takes types to types in our source programming language, right? And since our source programming language is, say, Haskell, right, where all types, so values are all first-class values, including functions, including computations, like monads, we always have to be dealing with first-class values that can be passed around. Okay, but there's there's really two aspects to the idea of a monad. There's the first-class part, which is that we can pass it around as data, but then there's this sort of computation part, which doesn't inherently mean that you could pass it around as a first-class value. And interestingly enough, you can tease apart these two aspects using the notion of an adjunction from category theory. Okay, and the idea of an adjunction, specifically in these call by push value models, is that instead of having one kind of types, we're going to have two different kinds of types, which are what I call the value types, which are like the first class values, and then the computation types, which are, you can kind of think of them as second class types in that something that has a computation type isn't yet a first class value that you can pass around, okay? And then instead of having a monad, which goes from types to types, we have two type constructors, F and U. And when you compose them together, you do get, in fact, a monad, okay? So if you're familiar with adjunctions, you know that every monad, in fact, composes, every monad can be decomposed into an adjunction in more than one way, the Kleistli category and also the category of algebras, and vice versa, every adjunction induces a monad, okay? And so based on this generalization from monads to call by push value, we can generalize from the syntax of programming languages with monads and with adjunctions, okay? So if we go back to the 90s, we have early 90s, late 80s, we have Moji's computational lambda calculus, which was basically lambda calculus with an abstract monad in it on a Cartesian closed category. And in the late 90s, early 2000s, Paul Blaine-Levy developed this calculus called by push value, which is related to the strong adjunctions the same way that the computational lambda calculus is related to the strong monads. Okay, and so one way to think about what I want to talk about here is that if we look also in the early 90s to Phil Wadler's paper where he said, okay, monads are actually useful for structuring computations in functional programs. What's the corresponding construction over in call by push value? Okay, and so the corresponding construction is this idea of a relative monad. Okay, so let's talk in a little more detail about call by push value. So like I said, there's two different kinds of types in call by push value. There's the value types, which we can kind of think of as acting like types in a call by value language. And there's the computation types, which we can think of as acting like types in a call by name language. And Levy's intuition that he gives for this is he says, a way to think about it is that a value is and a computation does. So when you describe what a value type is, you describe it in terms of what are the values of that type. And when you describe a computation type, you describe it as what do the computations of that type do. Okay? So, for example, some simple value types here. So we have a tuple type, so this is like an eager product, a call by value product, right? And the values are just pairs of values. We could have a sum type, and the values are either injection, the left injection of a value or right injection of a value. And most importantly for us today is there's this U type, UB, and the values of the type UB, you can think of them, or Levy calls them thunks, right? And so it's a thunk of some code here, M, that has type B. And the way that I think about this from an implementation perspective is that UB means it's a closure, okay? Then we have the computation types. And so we describe a computation types by saying, what do computations of this type do? Okay, so first of all, we have the function type. And what it does is it pops an A value off of the stack, and then it proceeds to behave as the type B, okay? And then we have this lazy product, which I like to use the linear logic ampersand for, which acts more like the product in a call by name language. And the idea is that computations of this type B1 with B2, well, they pop a tag off of the top of the stack that's either a pi1 or a pi2. If it's a pi1, they behave as B1, and if it's a pi2, they behave as B2. So you can kind of think of this as like the computation supports two different methods. Okay, and then most importantly, again, we have the FA type, which says computations of this type can do whatever effects are allowed by my language, and then they can return A values at the end. And the way I just described it, it sounds in fact very similar to a monad, right? But the difference is FA is not a first class value type, it's a computation type. So you can't pass it around as a first class value unless you use this closure type as well. Okay, so here's the rules. These are really the only code probably in the whole talk for an F type and the U type. Okay, so the F type does in fact look exactly like a monad. So it says, if I have a value of type A, then I can return it to get a computation FA. And if I have a computation FA and I have a continuation for it in that uses A values, then I can do this monadic bind, monadish bind. Because notice here that the output type is any computation type B, not just a monad type. So that's the big difference between this F type and a monad. Okay, and the closure type is actually very simple. It says if I have a computation of type B, then I can sort of reify that as a first class value, a thunk that can be passed around. And if I have a value that's a closure, then I can run it, right, to get that computation out. And in this way, we can use call by push value to decompose the monad into two pieces. So T can be defined then as U composed with F. And Levy, when he originally developed this, was primarily interested in showing that you could embed call by value and call by name languages in this way. So for example, a call by value function type A to A prime is a closure that whose code pops an A value off of the stack and then does some stuff and returns A prime values. And call by name, on the other hand, says that a call by name function takes in a closure as an argument. So it takes in its argument as a closure. Okay, and these are closely related to Moji and Girard's translations of call by value into monads and Girard's translation of call by name into linear logic. Okay, so now back to the stacks, okay? So when I describe computation types Levy style as what they do, okay, Well, I mentioned this word stack a couple times, right? And a function A arrow B pops an A off of the stack. B1 with B2, it pops a tag off of the stack, right? So there's an alternative way to look at computation types, which is that computation types are stack types, okay? And so the idea is that every computation type, since it interacts with the stack, has to describe a precondition on the structure of the stack in order for the computation to be able to run. Okay, so A arrow B, as a stack type, we can say it's a stack that has an A value on top, and then the rest of the stack is B stuff. Okay, and then the product is, we said it popped a tag off of the stack and then behaved accordingly. But so as a stack, it should be a tag, say pi1, pushed onto B1 stack, or a pi2 pushed onto a B2 stack, right? And if you notice, there's a kind of duality here where the function type becomes a sort of tensor product and the product becomes a kind of a sum type. And this has been explored in things called enriched effect calculus. There's a nice syntactic way to view this as well. And so the one thing that's a little weird is this FA type should be a stack that represents a continuation for A's. Okay? And that's a little too abstract, right, for us talking about implementation. So there is a nice theorem, which I think is originally due to Muehlberg and Simpson, which is that, which is basically parametricity theorem. So we can church encode the FA type in the following way. We can say that an FA computation is equivalent to one of the type for all R, and the important thing here is R is a computation type. So for all computation types R, you give me a function from A to R as a closure, and then I will behave as an R, okay? And if we look at the way that this would be implemented in terms of the stack, this is we have a literal function pushed onto an R stack. But since we're parametric in R, we can think of it as this part of the stack is totally opaque to us, okay? Which is a very reasonable model of to a first approximation of how we do implement continuations on the stack. Okay, so now relative monads. So first the theory. So this is from a famous paper called Monads Need Not Be Endofunctors. And so the idea is that we first have a functor from C to D, and then we can define the J, and then we can define the J relative monads as some other functor from C to D that has something that looks like this return and extend of the monad, okay? Satisfying corresponding equations. Okay, and so so my proposal is that we think of these stack-based effects as being monads relative to the F type in call by push value. Okay, and so we have some type constructor which are called EFF, F, that takes value types to computation types, and then we have a return and an extend, which involve this linear arrow here. But we can actually eliminate, so this is like what the theory, the category theory tells you if you just do it and pop it out. But we can rewrite these to something slightly more familiar. So this says that return should take an X and be a computation that behaves as an EFFX. And then the extend says given a function from X to F of Y and an F of X, we produce an F of Y, and there is an important thing, which is that this function is linear in the F of X. Okay? And now there's actually a very intuitive interpretation of these ideas and the linearity in terms of stacks. Okay? So the idea is that EFFA, like our FA type, is some notion of continuation for A's that also allows us to perform whatever effects we want to do. Okay? And so return, if you view it as this linear function, well, flipped around in terms of stacks, that says given an EFFX stack, we can turn that into a continuation for X's. And then you could just return to that continuation. Okay? And then the extension part says that if I have a stack that has real continuation as in a function from X to F of Y pushed onto an EFFY stack, then I can compose those together to make an EFFX stack. Okay, so So the idea is that this is a model of the way that we implement the effects on the stack. Okay, so let's look back at our example. So our examples from earlier, exceptions and state. So the first example was this kind of naive implementation. We can still do that naive implementation by just composing the built-in F type with A plus E, right? And this is that original implementation I had, that we just have a continuation for the sum type. Okay, but by church encoding in call by push value, we can show that this is equivalent to the following computation type in call by push value, which just says for any R and any function from A to R and E to R, I'll behave as an R. Okay, which in terms of stacks just says I have the success continuation pushed on to the error continuation pushed on to the rest of the stack R. Okay? Yeah. And so what about the stack walking part? Well, that's a little more complicated, but the idea is that it's some kind of free monad. Okay? And so the free relative monad generated from G, which is a type constructor like our EFF in this case, on A is basically, I offer you the choice. I will behave as a GA if you want me to, or if you want me to, I will take a continuation from A to free X and give you a free A. I think this should be free X. Yeah, sorry. Okay, so that's a little confusing, but the idea is, and then I fixed it, this slide. So the idea is that we have some notion GA of stack. And so an element of this free GA, a stack for this, should be either a GA, right, the left side, or it should be a continuation pushed onto some more free GX stack stuff, right? And so unlike in the previous case, this rest of the stack is not abstract, right? And so in general, what is a stack for this? It's just a sequence of continuations that are sort of composable. Oh, and there I messed it up again. That should be X1. But if we then take, for example, free of the exception monad, of one of those exception monads that we picked, right? Then we get one where the stacks look like a stack that we could walk up, right? So it's a stack of success continuations, we could say, right, that are composable, but the error continuation is somewhere way far down in the stack, right? And so when you actually raise an exception, which I wrote the code here, right, you basically say, am I done? Which is this case, I have a success continuation and a failure continuation. Then I'm just going to give my E value to the failure continuation. Otherwise, I'm in one of these cases where there is no handler. So I'm just going to pop it off and continue raising, right? And so this encodes this stack walking exception raising that we had, which is what you get if you Google how to implement exceptions. Okay. And then for our state monad, this one is a little less impressive, but so we can take the function one, we say we take an S and we return an A times S. But again, if we church encode it, we get something where we say we have a continuation for an A and an S to an R pushed onto a stack that has a state S followed by an R, right? And so I would argue that this is essentially the an implementation of state where we've chosen a place on the stack where we're implementing this state cell, right? Okay. I wish I wrap up or yeah. Okay. So I'll skip all of this stuff. Relative comonads, what are that? Who knows? So what I'm wondering now is like, what should we do with this idea? Well, two different ways to do it would be, thinking of call by push value as a low-level source language, right? Then this should just say relative monads are as useful to us as monads are in languages like Haskell. But then also, if we think of as call by push value, we could think of call by push value as the basis for an intermediate language, right? Where we could compile multiple source languages. Then we could do things like different languages that have different effects. We can mediate between the different stacks that they use using relative monad morphisms, things like that. Okay. And so there's some takeaways for the talk, but I'd be happy to take questions.